Okay, so today we will look into non-smooth functions, the theory behind that. So to give you an example for non-smooth, there are many ways, but let us say some examples are, for instance, when I use L1 norm and sum of mod of xi, I equals 1 to d, and this is often used as regularizer. And since it's one norm, it's usually imposed, usually used to impose sparsity constraints. Okay, so let's say that promotes and then another one could be if you use activation functions like ReLU, so which is sigma t 0 if t less than equal to 0, and it's t if t greater than equal to 0. So this is defined as a function which is like activation function, but so it's t when, so it's like this, and then it is 0 until 0, and then like this. So this is the well-known ReLU activation function. Obviously, it has non-smoothness here. Okay, so we have seen non-smoothness in previous classes as an introduction, but here we will now go into theory, convergence, and so on. So another example would be so differentiable functions not being defined on entire space. Or in other words, it takes values, let us say plus infinity, outside the domain, so in this case I think we have also seen this case where we use an integrator function and we add it to the function values. So basically it's for constraint problems, and using integrator function we extend it. So in this case the typical example is the indicator function for some constraint C, which is a subset of RD. And indicator function, if you recall, it is delta Cx is 0 if x is in C, and it's 1 if x not in C. So that's the integrator function we recall. Oh, actually it's infinity, right? So it was plus infinity if it's not in C. So and such functions are useful basically to extend a given function over all of the domain. So useful because it allows um, minimizing f over all Rn or whatever. Okay, so basically it allows me to extend a function, because then I will extend the function by f plus delta c. Now it's defined over all of R. Although f is defined on, although f is although domain of f is C, f plus delta C is defined on all of Rn. So this kind of extensions also create a discontinuity, because function is defined, is taking valid values on C. So basically, if the constraint set is C, so function is taking some valid values, but then due to the indicator function, beyond this it takes infinite values. So there is a discontinuity here on these boundary points. So these are some examples of discontinuous functions. Now let us go through some definitions. So in the notes, it's definition 8.1, and it says f from Rd to R union plus infinity. Then we define the domain of f by basically all the valid points where it takes finite values. Is for formality we are defining this. And actually our goal is to define what is a proper function. So basically it depends on the domain. Okay, so basically domain should not be empty. Okay, then we say a function is proper. So f is proper if domain of f is not an empty set. Now I can recall the lower semi-continuity as well. So this is definition 8.2. So a function f from Rd to R. So here we are also looking at extended value, extended real valued system. So we are adding plus infinity as well, and x bar in Rd. So we say that f is lower semi-continuous at x bar if we have f x bar is less than equal to limit infimum of x going to x bar f x. So that's the definition of lower semi-continuous. So this essentially means that these functions are allowed to have discontinuity, but these are like this. So as I get closer to x bar, these values are larger than these values. Okay, so there is a jump discontinuity, but the jump takes the larger values on the right. Similarly, I can define upper semi-continuous. A function which is both lower and upper will be continuous. Okay, but for convexity, because we are proving results that goes well with convex, then lower semi-continuity goes well with convex. Okay, so So that's why we are interested in lower semi-continuous. So then in that case, we also, in sort, we call this LSC. Okay, so this is the sort notation for that. And here we said that it's lower semi-continuous at x bar, but then if it is if it satisfies this for all the values in the domain, then we call that the overall the function is lower semi-continuous. So you can define it point-wise. It's lower semi-continuous at x bar, but if it satisfies this for all the points, then obviously at the points where it's continuous, it's also lower semi-continuous. So that's fine. You only have to look at the points where it has jumps. Okay. So if the function is f is LSC at all x in domain of f, then f is called, so in this case we call it just the whole function is like lower semi-continuous at all its points. Okay, so that's lower semi-continuity. Now, so examples of these are 8.3. Let us say f from Rd to R continuous, then it is proper and LSC. So the continuous function is certainly a lower semi-continuous function. Okay, so that's given. So you can formally try to prove these things. C subset Rd closed and non-empty, then its indicator function delta C is proper and LSC. Okay, so these are the things you may try to prove. And a finite sum of proper LSC is proper LSC. Okay. So these are the examples of LSC. This includes essentially many class, because many functions are essentially jump discontinuity, and if the jump discontinuity is like this, then as you can see it includes a very broad class of functions. So, and we recall the subgradient and subdifferential. So we have done this like towards the beginning of the course. Just do some recall. So 8.2 subdifferential of non-smooth convex functions. So definition 8.4, f from Rd to R union infinity and x in Rd. So we say that eta in Rd is a subgradient of f at x in Rd if it satisfies the following property. So for all y in Rd, fy minus fx minus eta y minus x is greater than or equal to 0. So you can recall this, we have done this before. So if we recall a little bit, the idea came from when we were discussing convexity, and a function is convex when fy is greater than or equal to fx plus grad fx y minus x, and that essentially told us that that describes a hyperplane that's a tangent to the function, and it's a lower bound. And subgradient is any line that can be a tangent. Okay, So basically any eta that you could find, the slope of a function, okay, which can become a lower bound, you can define that to be a subgradient. Okay, so we have done this in the previous classes, so you can always see those videos. So here we are dealing with non-smoothness. So something like this. So there will be a let us say tangent. I mean, not necessarily. It could be something like this, where there is a kink here. So there is a non-smoothness here. Okay, so you can say that there could be multiple tangents that could be drawn here. So what subgradient says that it is convex, so I certainly have a guarantee that there is a plane which is a lower bound. But then to define the subgradient, we are saying that, okay, collect all those planes that can act as a lower bound with the slope eta, and that is how the subgradient is defined. Okay, so if you can recall this, we have discussed this before. So that's the definition of a subgradient. Okay, so subgradient is when I mean one of the gradient, I will call it a subgradient, but if I collect all those eta which could act as a global lower bound, then we will call it a subdifferential. So hence subdifferential will be a set. So we denote the set of all subgradients. Okay, so today I am using some other chalk, so my handwriting may not be like before, but it is fast, I see that, so it's good. So so basically it is a set of all subgradients at the point x. Okay, so we can define this as Rd for all y in Rd. Basically we have that, so Fy minus Fx minus eta y minus x greater than or equal to 0. Okay, so basically we collect all those eta. So this forms collection of all the subgradients at the point x. So del f x is the subdifferential of f. We can also collect all the subgradients at all the points. Okay, so that can be written as, then we drop this x, so we basically collect all the subdifferentials. So this is in Rd such that del f x is not phi. So basically collect all those x, So the way it is like all the points where the subdifferential is not empty. Okay, so it's not the collection of all subdifferential, but the point x for which subdifferential is non-empty. Okay, so subdifferentials are guaranteed to exist whenever f is convex and continuous. You have lemma 8.5. It says that f from Rd to R union infinity is a convex function and continuous at x in Rd, then the subdifferential at x is not empty. So the proof of this, we will skip this. It's in the reference 33. So I leave this as an exercise basically. Okay, so you look up this proof. So what it says is that for convex and continuous function, subdifferential will exist. Remember that there is a convex also written. Okay, so basically here we are looking for planes that are global lower bound, right? It can only happen if it's convex. Okay, so if it goes down like this, then there will be a problem, because here this is not a global lower bound for, because these points are going down. Okay, so this result is for convex and continuous. So you have a guarantee that at each point you will get some gradient, or at least subgradient. And actually we have done this proof before, so this one I will skip, which is saying that if it's differentiable, then the subgradient is the actual gradient. So this proof we have done before. So this is lemma 8.6. So f from Rd to R union plus infinity is a convex function that is differentiable at x in Rd, then the gradient subgradient at x is nothing but the actual gradient. Okay, the proof of this very luckily we have done, so we will skip the proof. So this also suggests that the way we defined subgradient definition is a good one, because when the function is differentiable, subgradient does give us the true gradient, the unique gradient I mean. Okay, so now let us prove something called Fermat's theorem. Fermat's theorem is also, I believe we have done this. So it's a French name, so we don't pronounce the T. Okay, it's Fermat. So if it ends in T, we don't say that T. So let f from Rd to R union plus infinity and x bar in Rd, then x bar is a minimizer of f if and only if 0 belongs to the subdifferential. Okay, so I believe we have done this proof as well. So what it says is that even for the non-smooth case, it is possible that you will have many gradients, but for the at the minimizer you must have one of the gradient which is 0. Okay, so basically we can picture this as okay, so this is the point where it's not differentiable. So at least I will have one gradient, although I have many other gradient, but at least there will be one gradient with slope 0. Okay, if that point in our case it's the x bar, if the x bar has to be minimizer, then there must be one of them which is flat. Okay, so although there could be many, that's why we are writing 0 belongs to the gradient set. So we have done this proof where the proof is like 2 lines, so I will just very quickly do this. X bar is a minimizer of f, implies and implied by for all y in Rd fy minus fx bar is greater than equal to 0 because x bar is the minimizer. So for any other point y, it must be greater than equal to fx bar, and this implies an implied by, and we somehow bring in the that guy but with eta 0. Okay, and because it will satisfy that with eta 0, I will just plug in here minus 0 y minus x bar, and hence it will prove that 0 must be the, because it will satisfy the inequality. So this is same as minus eta 0 I will take, and then y minus x bar. And this is true for all this is true for all y, so hence 0 must be the, according to the definition there, 0 must be the subgradient, okay, at x bar. So this implies an implied by 0 del f x bar, and there is a slight mistake here, but it's fine. We have this. So this is also, we have done this, which is the sum rule, f from Rd to R, convex, differentiable, let G from Rd to R, union plus infinity, which is proper and LSC and convex. Then for all x in Rd, del, so what is the, basically this result is sum rule, so basically subdifferential of f plus g. So some of you will recognize that this, we have done this before, plus del gx. So this is a set sum here, right, because g is not necessarily differentiable, so this means that del g here could be a set. So here you, what it means is that since f is differentiable, so this will be unique, so this will be single number here, it will be added to each of the subgradient of g at x. Okay, so that's like the set addition going on there. Okay, so so we have seen this before, but if you want to see a full proof, then again C33, okay, for a proof of this. And then lemma 8.10, which is a simple result. It says that f from Rd to R, proper LSC convex, and x in Rd and gamma greater than equal 0, then it says that del gamma f at x, so basically gamma can be taken out. This is easy to prove. Okay, so you can verify this directly from the definition. Okay, so prove it directly from the definition, follows from definition. So this will be a homework. Okay. Okay, so now we can also extend strongly convex function in the non-smooth case. So let us extend the ideas of strongly convex, smooth. So this is 8.3. Non-smooth strongly convex functions. Okay, so lemma 8.11, it says f from Rd to R union plus infinity, proper LSC and mu strongly convex, then F admits a unique minimizer. Okay. So this uniqueness proof I wrote some time ago. I skipped it, and I will skip it again. I will keep it maybe if I will have time to do this. For the moment, I will just skip this to go through. Well, the proof is a bit long. Okay, so so then we go to lemma 8.12, and so here we will see the consequence of LSC and mu strongly convex. So this will give us some inequality. So F from RD to R union plus infinity proper LSC and mu strongly convex then for all x y in RD and eta in del fx in the subdifferential of f, we have the following inequality. So this is fy minus fx minus eta y minus x greater than equal to mu by 2 y minus x whole squared. Okay, so for a function which is proper LSC mu strongly convex, then this inequality holds. So let us prove this. So define gx to be fx minus mu by 2 x square. So you can see this what I am trying to do, because I am trying to define, we have seen a result previously that if fx is convex, or let us say gx is convex, then gx plus mu by 2 norm x square is mu strongly convex, and it's an if and only if statement. So this means that if f is mu strongly convex, then gx will be at least convex. Okay, so if you can recall this statement that we have done some time ago, so gx is still guaranteed, although I am subtracting minus mu by 2 norms x square, it is not guaranteed to be mu strongly convex, but it is guaranteed to be at least convex. So so according to lemma, so this lemma is like 2.12 in the notes. So according to lemma 2.12, G is convex. It is also LSC and proper. So lower semi-continuity won't get disturbed because the original function f is lower semi-continuous. By subtracting from norm x square, it doesn't change that. So this remains LSC, G remains LSC and proper. And according to the sum rule, we can also look into the subgradient of f. Okay, so the subgradient of f will be basically subgradient of g plus basically mu x. Okay, because the second derivative of this is differentiable, so derivative of that is mu x. So differential, so subdifferential of f del fx is del gx plus or minus mu x. or no, sorry, so this I'm taking f, so it goes there, right? It becomes plus mu x. Okay. So remember what we are supposed to prove is this guy. So now we will try to prove this. So basically f is defined in terms of g. Okay, so that's what we are trying to leverage here. So in place of f we will put g's. Okay, so let us start from the left hand side. So we have fy minus fx minus eta y minus x. We will just write the f in terms of g, I guess. So it will be fy will be gy plus mu by t norm and so on. Okay, so let us do this. So we have, so in place of fy, I have gy plus so this is the fy term minus fx. So fx will be minus gx minus gx and then minus mu by norm x square, and then we had this inner product term which is minus, yeah, here we don't have to do anything, eta y minus x. I mean one of the eta could be the gradient of the subgradient of f. So I believe we will replace eta by del fx, which is del gx plus mu x, and we will separate out the gx, gy and del gx, and g being convex, that will be greater than equal to, and remaining term that you will be left with is mu by 2 norm y minus x, right? So in place of eta we can choose this del gx. So okay, eta this is for the subgradient of fy. So basically this will be del gx and del gx plus mu x and then y minus x. We have from here at least we can separate out the g's. Okay, so gy minus gx minus del gx y minus x. So let us keep this guy separate because we know that this guy is supposed to be greater than equal to 0 because g is convex. Okay, so this and we have to prove greater than equal to in the theorem. So this will give us greater than equal to sign. So that's good. And what is remaining should boil down to mu by 2 norm. I see mu by 2 x square, and another thing I see is negative of mu x y minus x, right? So I believe it gets into the square form. Okay, so we have to complete the square basically. Plus I mean also minus mu by 2 okay, so we can split this. At least what we have is this greater than equal to 0, so I will get rid of this. So this guy is greater than equal to 0 because g is convex. So what we are left with is yeah, there is a negative sign, but let us keep that, mu x y plus mu x x, okay, minus mu by 2 norm x square We missed that, right? Oh, there, yeah. There is this mu by 2 y square also sitting here, right? So we missed that, and that should complete the square, but let's see. So I will have this plus. Okay, there is one plus, and then there is one minus here, but then I think the minus one gets cancelled because of the second term there. Okay, so let us work out this. So plus mu by 2 norm of y squared. So this guy gets becomes mu by 2 plus mu by 2 norm x squared. Okay, so this guy becomes, so this is equal to minus, you can take this mu out, xy, and this minus this is plus mu by 2 norm of x square plus mu by 2 norm y squared. So this completes the square. Okay, so this is exactly mu by 2 norm of y minus x whole square. Okay, so hence the proof. So now let us look into 8.4. We introduced something called proximal operator. This is a very good idea, and it is used a lot in doing analysis. So next is 8.4 is called proximal operator. So proximal operator, via proximal operator you can go to something called fixed point. So SGD could be seen as a fixed point method, and many method could be written like this. So it somehow connects to fixed point theory, contraction mappings. So you can generalize basically. So definition of a proximal operator. So definition, and this is definition 8.13. G from RD to R union infinity be proper LSC convex. So we define the proximal operator as follows. Define proximal operator of G as a function prox G from RD to R as follows. Prox G takes the argument x, and then it does the argmin. So there is a small optimization problem involved here. RD G of x prime plus half of x prime minus x whole squared. So this is how a proximal operator is defined. At a point x, it's the argmin of x prime in RD. So basically you solve an optimization problem. So we will see a lot of use of this operator. Okay, for the moment it looks strange that what is the use of this, why did we add this term here, right? And that's also kind of suggests the name like proximal. Okay, so we are looking at something closer to x. So we will see a consequence of this. So a proximal operator is well defined because if G is convex, then this will keep it, in fact it will make it even strongly convex. Okay, because if you just forget this shift part, so it is similar to like this. So if it is a convex function and if I add mu norm x square, then it makes the convex function mu strongly convex. So in this case you can have same thing. If G is convex, then if I add norm of x square, then it will even make it strongly convex. So it is well defined because if it's G is convex, it's even strongly convex and proper, and all those hold here. Okay, so proximal operator is well defined. Well defined since Gx prime is convex, the sum Gx prime plus half x prime minus x square is even strongly convex. Strongly convex. So there exists a unique minimizer also. Okay, so when I am solving for this argmin, in fact there is a uniqueness of a minimizer. So that means that it's a well posed. Okay, in when working with many math problems, sometimes people say, is your problem well posed? That means, does the solution exist and is it unique? So people working on PD, they use this word a lot. Okay, so let us see some let us see the usefulness of these, but first we will see an example of a projection 8.14, and projection is a proximal operator. So let us say that C is a subset of RD, non-empty, closed, convex set. I have never went into topological aspects like closeness and so on, because at first sight you may get away with that, but closeness in general guarantees use in some way minimizer and so on. Okay, so but you can skip for the moment. So let delta C be its indicator function, then the proximal operator delta C. So indicator function, right? Let us define indicator. So basically this is our C, it's a subset of RD. So delta C of x is 1 if x is in C, and it was, I believe, plus infinity if x is not in C. So that's the indicator function, and what we are saying is that the proximal of this. So proximal operator is defined for a function, right? So in this case we define proximal for a function g. So what we are saying here is the proximal. What would be the proximal of an indicator function? Okay, so let us write that. So proximal. So we have defined this, or should be? Are we going to define? So proximal operator. Well, we will use the same notation. So prox underscore subscript. So let us write that prox of subscript of delta C, and we are trying to define that. So this will be argmin of x prime, and then delta C of x prime plus half x prime minus x squared. And this we are doing it for all of R here, let's say. So I mean the indicator function is defined for all of R, because either it goes in C or it doesn't go in C. So essentially it covers the whole space. So basically what is this, right? For what is proximal for a proximal operator for an indicator function? So if I see this, then if x prime doesn't go in C, then it's infinity, but I'm looking at the argmin, right? So that's not a very interesting case, because I'm looking for a minimization. So definitely x prime out of C won't be an argmin for sure, because that's leading this to infinity. So I have to look for x bar in C. So if x bar is in C, then in that case this guy becomes a constant, which is 1. Okay, so essentially everything boils down to, so to do it here, so if x bar is in C, then it's infinity, so so no use. Okay, so then we look for x bar, I mean x bar not in C, then it's infinity, but so hence we look for x bar in C. So for x bar in C, this guy delta delta C x prime is constant. So constant has no role in the optimizer. So basically you, everything boils down to argmin of this. Okay, so here it's RD, but then eventually it's arg min of x prime in C, half of x prime. So basically what does this mean? This is saying that basically it's a projection problem. Given a point x, I am asking for what is the point x prime in C which is closest, right? So this is my x prime. So this became a projection problem. Okay, so that's what this example says, that proximal of a integrator function is basically a projection problem. Okay, so and proximal is defined from RD to R. Okay, so here I'm taking x to be anything, and for that x, if I'm looking for proximal, then essentially I'm saying this x, what is the x prime in C for which that x prime is closest to the x. So this exactly means projection, right? So that's an example, and so let us prove some results for the proximal. So lemma 8.15, G from RD to R plus infinity, proper LSC convex, and let xp in RD, then p prox of g x if and only if x minus p is in the differential subdifferential okay. So g is a proper LSC convex function, and we are taking some x and p in RD. Then if p is a proximal computed at x, then x minus p happens to be in the subgradient. Okay, so this may not be very straightforward for you to see now. Okay, so x minus p has to be in the subdifferential of g at p. So we will try to prove this claim. So if p is in the proximal of g at x, then this means that it has solved that argmin problem, right? Because proximal computing proximal is an argmin problem. So this means that its p is the minimizer of that argmin. So p is equal to prox of f at x if and only if p is the minimizer of phi u is equal to gu plus half of norm of x minus u squared. Okay, so that's clear from the definition. If p happens to be the proximal, then p must have minimized this. Okay, so basically the argmin of this must have been p. Okay, So that's from the definition of the proximal itself. So G is proper and LSC, all this is like already there, so I don't have to but the fact that it's proper and LSC and convex, we can use proposition 8.8 that I believe it's a Fermat's theorem that we did. Basically it says that at the point where the minimizer is achieved, there should exist a zero subgradient. Okay, so 0 must belong to the subdifferential of G. So basically if P is the minimizer, then it should belong to the subdifferential of phi basically. Okay, so because P minimizes this, so P must belong to the subdifferential of phi. So that's the Fermat's theorem that we have done before. So since G is proper LSC convex, phi is also that. Okay, so since G is proper this implies phi is also proper LSC convex. So hence the Fermat's theorem also applies to phi, and since P is the minimizer of phi, P must belong. Zero must belong to the subdifferential of phi at P. Okay, so this implies 0 belongs to subdifferential of phi at P. What exactly is the subdifferential of phi? Let us calculate that by the sum rule. So one of the guy is differentiable, and this may not be differentiable, but the subgradient will exist. So del phi is del G. So del phi at P is del G at P plus P minus X, because at U we are substituting P, right? So hence if we take a derivative of this, this is basically U minus X, let's say, and then in place of U I will put P. So it's plus P minus X, okay. Because this guy is differentiable, so there is only one unique gradient. That's why we just write this as a singleton set, but this could be a set of derivatives. So then this means set addition. Okay. So I guess we are very close to what we wanted to prove. So how do we relate to there, right? So if P belongs to the so what we are supposed to prove is this, right? So P is the minimizer, then X minus P. So if P is the minimizer, then X minus P must belong to the subdifferential of G at P. Okay, so at least like I can read one entry from there, although these guys are set. So at least 0 is there, right? And at least 0 is there. So point wise I can read out one of these, right? So P minus X or X minus P, if I bring this guy there, then X minus P, if we read as I mean there are many entries there, but what is useful for us is we will pick the 0, 0, 1, okay, because 0 is there in this set. Or if you want to see in another way, I mean, so I just use it from here, right? So 0 belongs to this, hence 0 belongs to this. So since 0 belongs to this implies X minus P belongs to, okay, hence proved. Okay, so let us see that as I said, proximal leads you to fixed point. So let us see that view now. Non-expansiveness. It's interesting that if I'm looking at the fixed point iterates, then what I am essentially looking for are the contraction mappings, but then this is not exactly a contraction, because any iterative algorithm I'm working on, let us say, and this gives me an error k plus 1, and if this iterative algorithm works like this, okay, many iterative algorithms could be written like that, then obviously my new error, if it has to decrease, then this operator somehow will play a role, because if I take a norm, okay, so it may become less than equal to, let's say. So now this guy, if it's a contraction mapping, then basically the norm of this guy is less than 1, okay, or something like that, okay. So a special case would be linear operators, then the two norm will be the max of the eigenvalues. So if the eigenvalues are all kind of less than 1, then this will make the current error lesser. So your new error will be lesser than the old error, and there is a guarantee, and that happens because the operator that is giving me the new error is a contraction mapping, okay. So expansiveness is not necessarily a contraction, okay, but we will see how it will help in the proof. So non-expansiveness is defined like this, basically one ellipsis, okay. So let's see. So this is the so let G from, so we will show that the proximal operators are non-expansive. So it may not contract. What this means is that it may not contract, but at least it doesn't expand. So that's why it's called non-expansive. So it will not increase the error, okay. So it's like that. So G from RD to R proper LSC convex, then prox of G from RD to R is one ellipsis. That's what non-expansiveness means, and we all know what one ellipsis means. So for all xy in RD, what this means is prox G y minus prox G x is less than equal to norm of y minus x. So basically it's one ellipsis because there is the ellipsis constant is 1 here. So repeatedly applying proximal, as it seems that it may not decrease, but at least it's not expanding compared to y minus x. So that's why it's non-expansive. We will see this, all these things, how it's used later on. So let us prove this, that it's a non-expansive operator, okay. So proof. So let us define Py prox G of y and Px prox G of x. So these are shorthand notations, okay, just to make it cleaner. And from the result that he had previously is if P is prox of G at some point, then that point minus P is in the subgradient. That's what we proved. So hence from here I can say that y minus Py is in the subgradient of G, and here I can say that x minus Px is in the subgradient of G at Px. okay, and y minus py is in the subgradient of g at py. So we will use the previous theorem. So this immediately implies that x minus px is in the subgradient of g computed at px. From the definition of the subgradient, we know that this is one of the subgradient. So we will now apply the definition that this being the subgradient of g. So what does it mean, right? So we'll just apply the original definition of the subgradient, and in place of x and y we will use these 2 points. Okay, so if you remember, it was gy minus gx minus eta y minus x, and eta was any subgradient. So here we found one of the eta, okay, and in place of gy I will take py, okay. So g of py minus g of px minus inner product of, in place of eta I have found one of these, so I will take that. So in place of eta I have x minus px, inner product with py minus px, okay. So that's what, so we are going to now use the definition of the subgradient now. So from the definition of the subdifferential, we obtain g of py minus g of px minus x minus px py minus px, and this is greater than or equal to 0. Okay, the definition is for any y and x, right? For our choice we took y as py and x as px, and so this holds. And then similarly we can do it for we did this for I believe we did this for the px. The same argument will hold for py. We will get another inequality and we will add those two inequality, okay, and from there we will somehow arrive at that. So similarly, from py is prox of g y, then this is g of px minus g of py minus y minus py, px minus py is greater than or equal to 0. So let us say this is our equation 1, this is our equation 2, and adding 1 and 2, so if we add 1 and 2, you can see g gets cancelled, right? So g plus gpy minus gpy and plus gpx minus gpx gets cancelled, and we are left with, we have to do some algebra a little bit, but let us do that as a first step, that we just add these two guys. These guys got cancelled. So this is minus x minus px py minus px minus y minus py px minus py greater than or equal to 0. Okay, and then we are supposed to we can multiply by the minus on the both sides, and we have to do some rearrangements, because in px and py it's hidden what we are looking for. So px was prox g of x and py is prox g of y. So these things are hidden, and x and y we can move them on the right. We multiply by the minus so that we get that less than or equal to. Okay, so we can do 2 steps at a time. Multiply by minus, then it becomes less than or equal, and x and y also we move it on the right. Okay, so but if we move it on the right, they are not in a clean form, right? Because they are paired with py and px, so we may have to apply some additional inequalities, right? So the first step indeed is, I will get rid of that minus and do some simplifications. Less than equal to 0. Now we will move these x and y. We have to have x and y there. It seems like Cauchy-Schwarz, when we apply, norm x norm y minus x will appear, but then we need to get minus, and I mean it's fine because here I'm looking for py minus px, so I will get 1 minus from here, so that these arguments match, and then I will move them other side. The first thing is to ensure that I have and I can see py minus px norm also coming up now, because there is also py minus px. Okay, so it's almost there. So let us yeah, we can use this. So if we look at that, then what we can do is, since we are looking for py minus px, so we'll change the sign here, and this argument will become common. So py minus px, and then I will have x minus px minus y minus py. So x minus px minus y plus py, y plus, okay, I hope it's correct. So x minus px, and then I took a minus there, so then it became minus of y, and then plus py, and then the last second argument became common, so py minus px, and the here also it's py minus px. Okay, so this is like less than equal to 0, and this is py minus px plus x minus y py minus px less than equal to 0. So this gives me py minus px, and this we will keep it px py minus px, and then this guy we will move it there, but when it will go there, it will go with its second argument as well. So this will be less than equal to y minus x py minus px. Okay, so here certainly we have a norm of py minus px squared, and here we will apply the Cauchy-Schwarz. Okay, so let us say CS, then it will be norm of y minus x, and okay, then one of these will get cancelled, so it's fine. Okay, so py minus px, and one of these gets cancelled, and assuming that it's not 0, and so assuming that py is different from px, then in that case we can cancel, and then py minus px is less than equal to y minus x. So now you can expand this, and that's exactly the form that we are looking for. The proximal is a non-expansive operator.